We are going to look at another example problem here. This one relates to the introduction of friction. Okay. So, let us look at the problem. There is a sphere that is rolling down an inclined plane. The inclined plane is 4 on the horizontal and 3 on the vertical. The mass of the sphere is 16 kg or 160 newtons in force. The radius is 1 meter. There is an external moment that is acting on this sphere in the magnitude of 144 Newton meter. So, I want to first solve this problem without the external moment to see what we understand, and then we will solve the problem with the external moment. Okay. So, first let us look at the case without the external moment. Which would be the case of a sphere of side 1 meter rolling down an inclined plane. Okay, so, let us first draw a free body diagram. I have a sphere. This is the center of mass. There is a weight 160 newtons acting on the through the center of mass. And then at the point of contact there is a normal reaction force . There is a normal reaction force of some unknown magnitude n and a friction force F. So, this point is the center of mass is moving with an angular with a linear acceleration a and an angular acceleration alpha. So, this diagram captures all the necessary elements, all the forces, the friction force F, normal reaction n, the weight of the body, and the kinematic properties, the acceleration a and the angular acceleration alpha. So, before we can proceed much further, I have 4 unknowns, capital N, capital F, a and alpha. So, let us start by writing the laws of conservation of linear momentum. So, sum of all forces is mass times the acceleration. So, I am going to do 2 things. I am going to take all forces perpendicular to the inclined plane. I am going to write this force balance as 2 separate component level balances. The first one being the component of the force perpendicular to the inclined plane and a component of the force along the inclined plane. So, let us first do the perpendicular to the inclined plane. Then if I take all upward forces perpendicular to the inclined plane positive, the only such force is the normal reaction, and the downward component due to the weight that is pushing down on the inclined plane is this 160 newtons times the vertical part, which is 3/5, and that is equal to 160 divided by 10, which is the mass of the body, times 0. So, the component of the acceleration perpendicular to the inclined plane is 0. Okay. So, this tells me that n is equal to 160 into 3 over 5 which is 96 newtons. Now, taking all the forces down the inclined plane positive. So, this is force balance along the inclined plane. the forces acting down the inclined plane or along the inclined plane are 160 into 4 divided by 5, which is the component of the weight along the inclined plane, minus F. So, the friction force is acting, we have assumed it is acting opposite to the it is acting up the inclined plane. So, this is equal to the mass again, like I said earlier on, I am going to assume g is 10 meters per second squared. Times the acceleration. Okay, so, let us simplify this. So, this is my first equation that gives me the normal reaction, this is my second equation. Now, I can still write the moment balance. So, in this case I have assumed alpha to be clockwise since it is rolling down the inclined plane. So, I will take the same clockwise moments positive, sum of all moments about g equals I g times alpha. The normal reaction has no moment arm plus the 160, the weight of the body has no moment arm. The only force with a moment arm is the friction force, and that has a moment arm of 1 meter. Ig for a sphere is 2/5 times m, which is 160 by 10 times r squared alpha. So, from here we find that F is equal to 36 alpha over 5. I will call this my equation number 3. So, I have 3 equations, I have but a total of 4 unknowns. So, this is where we need a little more information on the kinematic state of the sphere motion. So, we are going to ask what is the kinematic state of the sphere motion. That is it slipping at the point of contact, or no slip at the point of contact. So, depending on which of these two is the kinematic state of the sphere motion, our approach from here on, the fourth equation which we need to complete the system of equations would be different. So, I will first write, I will start by assume no slip at point of contact, and we will solve this problem. So, if I have no slip, what that automatically means is that I have this sphere of some radius r. If this center of mass moves with an acceleration a and an angular acceleration alpha, these two quantities cannot be unrelated, because at this point of contact there is no motion. So, when there is no slip, then A equals R alpha, which for this particular case says A equals 1 times alpha, 1 being the radius of the sphere. So, this gives us our much needed fourth equation. So, let us write them down. I am going to ignore the first equation, because that is just telling me that the normal reaction is 96 newtons. I am going to write down equations 2, 3, 4 and solve them. 2 is 128 minus 5 is equal to 16a. Minus f equals 16a. This is our equation 2. 3, f equals 32 alpha over 5. And a equals alpha. This is our equation number 3, this is our 4. So, and these equations are we have 3 linear equations in 3 variables. So, we are going to be able to solve them. So, I will substitute (3) and 4 into 2, and let us see what we get. So, 128 minus 32 alpha over 5 is equal to 16 alpha, which implies that 128 equals 32 alpha over 5 plus 16 alpha. Or alpha equals 128 into 5 divided by 12. Okay. So, from here I can calculate what f should be. F equals 32 alpha over 5 So, this is roughly 36.5 newtons. So, this is the amount of friction needed. This is the friction force acting at the point of contact in order to achieve no slip. So, I will rephrase and say this is the minimum value, or let me actually say it the way I said it, and then I will complete what I was going to say. This is the value of f under no slip conditions. Okay. But typically between a pair of surfaces, let us say in this case the sphere and the inclined plane, I have a value of mu. So, if I rephrase and ask the question, what value of the friction coefficient is needed to achieve no slip? So, if I ask this question, then what I need to do is relate this f to mu times the normal reaction. So, I will say let f equals mu times the normal reaction. So, 36.5 equals mu times 96. We already calculated the normal reaction n to be mu times 96. So, from here I can calculate mu to be approximately 0.38. Remember, mu has no units. So, therefore, we can say mu has to be greater than or equal to 0.38 to sustain no slip motion, which is also referred to as pure rolling. So, let us just do some thought experiments. say mu equals 0.5. So, if mu equals 0.5, that means mu is at least 0.38, mu is greater than the critical value. So, this is like a critical value of mu needed. Mu is greater than the critical value. That under these conditions, what it says is that I will have no slip. That is the first observation. The second observation, the maximum value of F, as we know from elementary Coulomb friction modeling, is mu times n. So, in this case the maximum value is 0.5 times 96, which is 48 newtons. So, actually the surface at this point, of contact A, this friction force F can go to be as high as 48 newtons, but in reality I do not need 48 newtons of force to sustain no slip. Only F equals 36.5 newtons is sufficient to sustain no slip, which means that even though mu is 0.5, the value of F would be 36.5 newtons and the angular acceleration alpha would be whatever we get from this number. Let me just do this calculation. Which is roughly 5.71. Okay. So, if I now take for this case mu to be 0.5, I will actually only need 36.5 newtons to sustain no slip, and the friction force at the point of contact, even though it can be as high as 48 newtons, will only take on a value of 36.5 newtons, and alpha would be 5.71 radians per second squared. Now, say mu is 0.2, then what happens? The first conclusion you can say is that mu is less than the critical value of a Coulomb friction coefficient that is needed to sustain no slip, which means I will have slip. At the point of contact. That means the sphere will slip at the point of contact. So, which now means I cannot say that A is not equal to R alpha. This is the first thing that you get to know. That means what I wrote down for my equation 4 is now wrong, and I have to replace it with something else. But what I do know is that F max is now 0.2 times 96, which is only 19.2 newtons. F max is now 19.2 newtons, but I need 36.5 newtons of force at the point of contact to sustain no slip. Clearly we do not have. So, essentially these for the two surfaces, the sphere and the inclined plane, do not have sufficient friction between them, which means we will have slip, which also means that F in the problem, in the free body diagram, will take on the maximum value possible. That means the friction force tries to do its best to minimize relative motion at the point of contact. So, this is a purpose of friction at the point of contact. So, friction at the point of contact acts to minimize relative motion. So, it is going to exert its maximum force, which in this case is 19.2 newtons, and if that force is unable to bring the slip, which is essentially the relative motion at the point of contact, to 0, it continues to exert the maximum possible force. So, now let us go back and rewrite our 3 equations that we had. I will copy this from here and paste it here. What we found is that this is no longer correct for our equation 4. We will replace it with we still need an equation to complete this system of equations. So, we say F equal to F max, which in this particular instance is 19.2 newtons. So, now what we find is that I have 3 unknowns, F, A and alpha, and 3 equations, right. So, this is what used to be this is now my 4th equation, the correct 4th equation. So, I can solve these 3 equations. Now, 128 minus 19.2 equals 16 times A so which means A equals 6.8 meters per second squared. Equation number 3 is still valid. So, F equals 32 alpha over 5, which implies 19.2 equals 32 alpha over 5, which implies alpha equals equals 3 radians per second squared. So, just to get a feel for how this is going to behave, this point here is moving at 6.8 meters per second squared, and this is rolling at 3 radians per second squared. So, at this point of contact A, the sphere is moving back if you imagine the point G, the point G is moving downwards at 6.8 meters per second squared, and in relation to G, acceleration of A as observed by G is minus 3 times 1. That means the absolute acceleration of the point A using the laws of relative motion is that the absolute at the point A, which is the point of contact on the sphere side, is moving down at 3.8 meters per second squared. The ball is trying to move down. It is not perfectly sliding, but it is essentially rolling less than it needs to roll while it is sliding. So, the net motion is that the point of contact where the sphere touches the inclined plane is actually scratching the inclined plane in a downward sense. Okay. Friction, as you can see, is trying to bring that point to rest. It is acting upwards, but it is unable to. Okay. So, this is the case of sliding. It is not the sphere has a net sliding motion at the point of contact. So, now let us move on to our problem and look at the case with the moment acting on it. Let us go back to the top of the problem. there is an additional moment of 144 Newton meters that is acting on it. And now if you notice here, we are told that mu is half or 1 over 8. Let us see what this looks like. So, there is a net moment, there is an external moment. So, if you think of this as the front wheel of a car, the front wheel of the car is a driven wheel. So, there is an axle that is trying to drive the tire, and that engine torque creates a net moment of 144 Newton meters. You could think of it in that way. There is a weight which is 160 newtons, okay, and we are asked to find, and what we are told is that this point of contact has two possibilities. Let us look at this first and the second. So, the bottom line here is that if I am told what the friction coefficient is at the point of contact, that it is a half or a 1/8, that information right at the outset is useless. I need to know if the cylinder or the sphere or the object is slipping or not slipping. That is the kinematic condition, that is the question related to the kinematics that I have to first answer. Okay. So, the way to solve a problem of rolling motion or sliding motion is to first assume no slip, calculate the critical value of friction needed to sustain no slip, and then compare the critical value of friction to the actual value of friction coefficient that you are given in the problem. Okay. So, let us do that. So, the first step is to draw a free body diagram, and we are going to solve the problem assuming no slip. That is our first step. Okay, this is our free body diagram. There is a linear acceleration a and an angular acceleration alpha. So, we will go through the same process. The fact I am going to do a vertical force balance, vertical perpendicular to the inclined plane, and that says n minus (3/5) of 160 equal to 0, which also implies n equals 96 Newton. That did not change. We are going to assume downward force is positive and do a force balance in the downward direction. So, 160 into 4 over 5 minus f equals 160 over 10 times a. So, this says this also has not changed. So, I am going to call this two. This is my modified, this is my 1, this is my modified 2. The third part is going to be different because there is, I am going to assume clockwise moments positive. The only force that causes a moment is the friction force, and that has a moment arm of 1, plus there is an additional external moment whose value itself is 144 Newton meters. This equals, so I am going to write my, so sum of moments equals Ig times alpha. So, the first moment is due to the friction force, the second moment is the external moment. This equals 2/5 m r squared, m is 160 divided by 10 r squared alpha. This is my modified equation 3, and the modified equation 4 is coming from no slip, which implies A equals R alpha, which also implies A equals alpha. So, this is my modified equation 4. let me simplify 3. F plus 144 equals 32 alpha over 5. Okay, so let us now solve these three equations. If I substitute three and 4 into 2, I know from 3 F equals 32 alpha over 5 minus 144 128. So, from 2 minus 32 alpha over 5 plus 144 equals 16 alpha. So, this says 272 equals 112 alpha over 5, which implies alpha equals alpha equals 12.1 radian per second squared. So, this is if no slip, let us be clear about that. Okay, but the value of f is what I am really interested in, which is 32 over 5 into 12.1 minus 144. So, the required friction is approximately minus 66.2 newtons. So, under these conditions, we assume the friction force acts upwards. Look at the free body diagram. Okay. What the value of F has now come out to be negative, which means it is not really acting up the inclined plane, it is actually acting down the inclined plane, and its magnitude is 66.2 newtons. So, I ask the next question, what is the critical value of mu to sustain no slip motion? The answer to that is gotten by equating F equals mu times n. That means this 66.2 newtons. I can ignore the sign because in any case, whichever direction the friction force acts, the mu calculation would be independent of that. So, we can just take the modulus of the friction force equals mu times n, which implies mu would have to be of the value 66.2 divided by 96. So, it would have to be of the value 0.69. Mu would have to be of a value 0.69 before we see no slip. This is the critical value of mu needed to sustain no slip motion. Any less than this, we will have to do what we did earlier for the sphere without the external moment. That is, I cannot assume A equal to R alpha, I will have to assume A is not equal to R alpha, but F is equal to the maximum value. So, if I know mu is half, the maximum value of friction force possible is half times 96, which is only 48 newtons, but I really need 66 newtons in order to sustain no slip motion. Therefore, the surface would exert the maximum possible force on the sphere to bring relative motion to rest. It would still fail, which means F would be equal to 48 newtons, not 66.2 newtons. So, replace the fourth equation where we said A equal to R alpha with the correct version of the fourth equation, which is F equal to 48 newtons, and solve for the motion. So, let us complete that part. So, for mu equal to half, A, let us be clear, mu is less than the mu critical, which implies the sphere is likely to slip. So, what we now have is, again I will write down the four equations once more. Except this fourth equation is incorrect. Instead, what we have is F equals half mu times n, that is equal to half times 96, which is 48 newtons. So, if F equals 48 newtons, then from equation 2, 128 minus 48 equals 16 times A, which implies A equals 8 meters per second squared. We also know that F plus 144 equals 32 alpha over 5, which implies 48 plus 144 equals 32 alpha over 5, which implies alpha equals 30 radians per second squared. So, notice how if A equal to R alpha and if A equal to 8 meters per second squared, it is going to be moving with an angular acceleration also that is equal to 8 radians per second squared. So, you can see that for this particular case alpha is 30 radians per second squared, which means it is slipping, and so the cylinder is spinning faster than the no slip condition would allow. So, let us just see what the kinematic condition would look like at the point of contact. Ag plus A of acceleration at the point A is acceleration of g plus the acceleration of A as observed by g. This is 8 minus 30 into 1, which is minus 22 meters per second squared. So, that is at the point of contact the sphere is moving up the inclined plane because it is spinning faster than the no slip condition would allow it to spin, and that is the reason friction is now acting downwards. So, this 48 Newton friction force mu times n, which is the maximum possible friction force, is acting down the inclined plane. It is trying to minimize this motion, as it is trying to bring the relative motion to rest or to minimize it as far as possible, and the friction force essentially acts in full magnitude of 48 newtons to make that happen, but it is still unable to bring the relative motion to 0. The bottom line, I want you to appreciate the action of friction. Friction at any point is not opposing motion as a whole, it is not opposing the motion of the center of mass. So, in fact, in this particular problem the friction is acting down in the magnitude of 48 newtons and the cylinder is also moving down at an acceleration of 8 meters per second squared. So, the friction force is in fact providing the traction to provide the forward acceleration, of course in this case along with the weight of the sphere itself, but even in the absence of the weight of the sphere, this sphere would move downward, would move down the plane just because you have the torque which is creating a traction force. So, friction is in fact the cause of the forward motion in this case, or one of the causes of the forward motion in this case. So, friction in general does not oppose the motion of the center of mass, it only opposes relative motion at the point of contact and tries to bring the relative motion at the point of contact to near zero values. Okay. So, I hope this illustrated the value and the physical use of friction, the physical it gave you a physical feel for how friction works. Now, the problem statement had the same calculation proposed for another value of mu of 1/8. As you will see, 1/8 is also less than the critical value, and I would like you to take that as homework and complete it. Thank you.